Hi, everyone. I'm Nicole Moldovan from Lymba, the premier NLP company for working with graphs. Today, I'm going to walk you through how you can get unstructured data from various documents into a usable format in a graph, and then how we can query the graph with plain English questions to get meaningful answers. Just a little bit about us. We've been offering best-in-class NLP solutions since 2005. Initially as a research organization before evolving into a product company. At the heart of everything we do is K-Extractor, our comprehensive NLP development platform and configurable pipeline. It powers a variety of applications from regulatory compliance, document analysis, drug discovery, and chatbots. So what do we mean when we say a configurable NLP pipeline? Well, all of these steps are modular, and we can tweak them to get the exact precise performance we're looking for in our particular application. We start with the basics at the top with pre-processing and continuously enrich until we get to the right named entity extraction and semantic relations identified. We also like to start when possible with an ontology, whether it is an existing one or one that we created with our Jaguar toolset. And this helps us bootstrap the entire process through our onto as input method, which automatically creates lexical and semantic rules from the ontology. It's a nice way to get started, just so you're not starting from scratch. You're never really starting from scratch anyway, because we do have a lot of entities and relations out of the box with the vanilla version of Studio and K-Extractor. So this whole process is what's going to result in that coveted RDF or triple representation, that subject, predicate, object piece. And that's what ultimately is going to go into our graph database. Now, if we're working with labeled property graphs, we take an extra step at the bottom here to convert it into nodes and edges. Once everything is in the graph, we can then perform semantic search on top of it, natural language querying, or really build out an endless number of applications on top of the graph. And I'll show you a little bit about how we can use natural language querying today. So keep this pipeline in mind as we start to work through our documents, which is what I will show you next. So here we have a patient complaint as well as her medical history. And we see that we have the issue that brought her in today, that she came in with swelling of tongue and difficulty breathing and swallowing. And we have her history, including all of the medications and devices that she's taken. And it's a pretty comprehensive amount of information. We also have, to help us figure out what could be wrong with her today, information from the clinical trials of some of the drugs and devices that we've taken. And we could see that this document is in a semi-structured format with some tabular information. It also has a lot of information in both longer text as well as some shorter snippets of data points. Now let's head over to K-Extractor Studio, our developer UI, and see what these documents look like once we've annotated them. Now, this is, again, our developer UI, so we're not going to be expecting a healthcare professional to do this in this environment. This is where we are going to be working through our lexicons, edit lexical rules, and semantic rules, as well as the annotations. This is where we can tweak that NLP pipeline. And I'm not going to go into it in too much detail here, but this is exactly what we cover in the medical playbook if you want to try it out. So let me go back here to my documents. So here we have our annotated documents as they've gone through the NLP pipeline. And remember, we can keep editing until we're happy with the way these annotations reflect the entities and relations that are being extracted from the documents. So from the history of present illness, we see that Jane is a 77-year-old woman, and she's suffering from a number of pathological conditions, including coronary artery disease, type 2 diabetes, and hypertension. And this information, I can link it back through the alias in the ontology. I can also see all of the different relationships we have here. We have a patient. The patient is experiencing these pathological states. The patient is then prescribed certain drugs for these states. And these drugs have certain characteristics like a dosage. She's also been taking this drug, Altis, for 8 years. And we see that there's more and more relationships that we could be building throughout. From another document, we also know that she has a stent in place for her coronary artery disease. And we can see certain specifics like the delivery system of the drugs. So here we have one that is an IV, or whether it is received through some sort of puff or pill. Now, we want to look at the clinical trial documents and see if we can find a link between the symptoms that she's having here and her prescriptions that she's been taking. So the first clinical trial that I have is for Ramipril, which we know is an alternate name for Altis. It is an alias. And one thing that we don't want to take for granted here is that these are from not just different documents, but different sources of documents. And this is really where NLP and having that core ontology and pipeline helps to bring all of this data together, because they're really coming from disparate originations. So a few things to point out over here. So not only is the clinical trial here involving Ramipril, there's another drug as well, and we want to make sure that we're focusing on the one that Jane is taking and not the other drugs that were involved in the study. We also can see that we have certain relationships between these drugs and the dosages. And specifically, in this study, we have Ramipril being given at 10 milligrams once a day. So this is the study that we found that has the right dosage of the right drug that Jane has been taking. And there's some things that we see in the study that are interesting. We have relationship types that we would expect between these drugs and these dosages. We also have placebo studies. We have information about the demographics of the subjects or the arm group, the subgroup, and we have their gender and age and so on. Now, at the bottom, we have the information we really want to focus on, which is the serious adverse events. This is the symptom that we want to pull back to what Jane has been admitted to the ER for today, and see if we can find any sort of connections between the trials here and what she's experiencing. So in this case, we have the adverse event, like a pulmonary embolism. And again, we see that this is broken out by the relationships between these different concepts. So my pulmonary embolism event has the relationship of event reported on a certain drug. There was a number of subjects affected in that group. The number of subjects in the arm group is important to distinguish between which drug it was about. So it's not enough to just find the number of subjects in the group. So for example, for Ramipril, we had one subject in this arm group E2 that was affected with the serious adverse event pulmonary embolism. I want to jump over now to another document for the other clinical trial and show you how even another clinical trial can look very different even when it's about drugs. So in this one, I have a clinical trial that is also involving Ramipril. However, the key distinction here is that there was a dosage change. So we see that the drug increased over time, and we have people going from -5 milligram tablets to 10 milligrams. We also have people changing other dosages throughout. And what's important here is that we can't just search the document and see whether there is a MG label. We have to see whether there is a specific increase, and this has another relationship. This has a dosage change which happened between these two pieces. Now, if we don't like the way that the rule looks, this is where we have a clue as to where we could go back in Studio and make changes to those rules. And again, if we find that there aren't enough relationships between the concepts we want, we go back and we annotate until we feel that this is reflecting how we want this to be ultimately in the graph. Lastly, I do want to point out the other clinical trial, which is about a stent. And you'll see that this one is a little bit different as well. So we've seen two trials so far that are quite different, even when they are about drugs. And now we have the stent. And we see here that we have a medical device. So this is for a prokinetic energy stent. But what allows us to compare these more like apples to apples rather than apples to oranges is that we've used the same relations that we did for the medications in here as we do for the stent. So we can also see the serious adverse event and how this medical device affected the different subjects. So in this case, we have some serious adverse events. We have the number of subjects in the group that were affected a little bit higher here, event reported arm, or event reported on, the arm group, and so on. So again, that's how we're able to use NLP to kind of normalize our data, even though they're coming from not just different sources, but also have some fundamentally different characteristics. Another thing that's important to mention here is that we're talking about serious adverse events. Now, we do have some instances in here of cough as a symptom, or maybe just an adverse event, but the ones that are really driving us today are the ones that are these serious adverse events. And again, the level of severity is subjective, and it could be something different that, depending on the ultimate use case, you might want to tag differently and process it differently in the pipeline. Let's say we've tweaked our rules and we're happy with the way everything looks, meaning our document's correctly marked up and the pipeline is representing the types of information we're looking to populate in the graph. Well, then I would set my pipeline and I would run my whole universe of documents through K-Extractor and output that into the graph. Well, graphs are great, but typically we have an end application beyond just creating the graph. If I were an end business user, like a healthcare professional searching through this information, I'm not going to do that in K-Extractor looking at annotated documents, nor do I want to be writing SPARQL queries. I want to use a friendlier interface, and this is where I would use Lymba's NL2Query. So NL2Query is UI agnostic. I'm going to show it today in a simple question answer search bar type of interface, but this could be plugged into a chatbot, a medical diagnostic system, or any other application sitting on top of the graph. What's important to think about when we're running things through NL2Query is that we're going to be asking questions from a source of different documents. And we're going to be asking them in plain English or natural language, and then letting the application turn that into SPARQL, the querying language of our graph. So let's start with a simple question. And this is going to be one with the answer from just the patient history. And we'll start with, what is Jane Doe prescribed and with what dosages? So we see here, we get the answer back, and this is reflecting the fields as they were in the graph. And Jane Doe was prescribed Altis, and specifically in 10 milligrams. The SPARQL query behind the scenes is going to be converting that question and then looking for the best answer in the graph. To take a look at that from an annotated perspective, again, it looks very much like our source documents once we've run them through the pipeline. We have our patient, Jane Doe. The patient is prescribed that prescription. So we have prescription as a class, and then we have instances of the class. And we have dosage, which is another class. The _G denotes that it is the class. So again, all of these rules are coming into play again, as well as the ontology. Now, that was kind of a simple question that just had an answer from the patient history, but what if we want to ask something a little bit more complicated? Let's go ahead and ask, what serious adverse events were reported across all of our clinical trials, and how many subjects were affected? So in this one, you'll see that we're now asking questions from an aggregation of the clinical trials. And again, we're seeing the information from the source and what that would look like if I wanted to click on the specific source document. It's going to bring me back specifically to that clinicaltrials.gov. Now, if you're doing this in some sort of, business application that is within your own system, maybe you want to tag a specific section of the document, and you can really play around a lot with that UI. It's nice for you to go back to the source. You can also go back and see how that question appeared in the, where that data appeared in your annotated document. But this is again combining from all of the different clinical trials, what the events were and the number of people. So we know if this is anything we have to be concerned about. That is going to look, again, very similarly, where we have the serious adverse event. Again, the relationship. So we know adverse events have number of subjects affected, and it's across all of our clinical trials. Now, another thing that we might want to ask as we go along is something that combines the information across the clinical trial as well as the patient history. So maybe I found now the clinical trials that are focused on the conditions that Jane is experiencing, and I want to ask something that is really pulling this all in together. So here, when I ask these questions, one thing to note is that now we're starting to combine and make those hops in the graph between disparate data sources. So we're getting the conditions that Jane is experiencing, and then we're searching for those conditions in the graph to narrow down which of the clinical trials are going to be relevant. These SPARQL queries start to look a little more complicated. But in general, we like to see that these all come back from the graph, right? We have patient is experiencing, those trials have a focus. There are specific pieces of information here that represented in the SPARQL query look the same when they are in the annotation. Right? Again, we have the clinical trials focused on the condition that Jane Doe is experiencing and the rule and relations that brings them all together. Now, maybe I want to find out if not just there were adverse events, but is this something I'm really going to be concerned about as the healthcare professional? I might want to ask something like, how many subjects were affected by these adverse events, reported on medications with the same dosages as Jane Doe, because again, we want to make sure that this is the 10 milligram dosage of our patient. So we're extracting here our patient name, our dosage amount of the prescription, and specifically the serious adverse event. Now, just think about the complexity of this query and why this is really interesting that we're doing this all automatically. The number of factors that would need to be considered multiplied by the number of documents that you would need to look through would never be feasible to look at in a clinical setting with a quick search type of question like this. We're looking at information from the history of present illness to find those adverse events and tying them back to multiple clinical trial documents. So here, the ER doctor sees that Jane's been taking her 10 milligrams of ramipril or Altis for hypertension. And there are indeed related to current symptoms, swelling and pulmonary embolism. And these counts are there, but they might be a little bit too low to ultimately show that there's any real cause behind this. The ER doctor then, with his or her medical opinion, can consider the likelihood of Jane's current symptoms being caused by ramipril. Some other things to note here that are interesting. We're not trying to make any medical calls, but these sentences across documents, including this last one here, are coming from a variety of semi-structured and unstructured data. They're coming from a similar governing body or the same governing body, and they're a great example of how we take for granted all of the calculations our mind do in the background to make sense of natural language. If you were to dump these files into SharePoint or try to do a keyword search, even force it into a relational database format, it'd be very difficult to make these connections between the data in a meaningful way. It would also be far less flexible if you then wanted to change how you represented the data. Maybe you overfit initially to cover only drugs, and now you want to expand it to medical devices. So the NLP pipeline takes all of this into account to break down these documents, starting at that pre-processing to the tokenization, entities, and finally semantic relations. When we now add these relations on top of relations, the medications with the dosage from Jane Doe plus the clinical trial information, that's when we really start to see that value and create that semantic web that we've been talking about this week. So that's what I wanted to show you today. And of course, it's a snapshot from an immense amount of documents. Jane is 77 years old. She's been alive for a long time. She has a lot of conditions, medications, devices, and those all interact with one another. The data on how these treatments affected other people can be buried through different documents and stored disparately, which makes it quite complicated. But by using NLP with your graph and letting the pipeline do a lot of that work for you, you can hopefully make it less complicated and get more out of your data. Thanks for watching from Lymba. Please reach out to us with any questions or for help on your next project. To receive a free consultation, email us at info@lymba.com, where we can customize a demo to suit your needs about your specific situation.